Alright guys, so last section in chapter 7, 7.4 on electrical power. So just a couple of things to consider before we get started. Why do you guys think at petrol stations there's signs that say to turn off your mobile phone? And why do you think that if we rub a plastic pen on our sleeve we can generate a voltage of 10,000 volts, which is a massive amount of voltage, but why does the resulting static electric shock not kill you or not cause you any harm? So it's all about to do with power, which is the transfer of energy from one place to another. So we're going to look today at what are the factors that determine the amount of power in electrical circuits. So we're going to investigate power and we're going to learn how to calculate the power in an electric circuit. So we need to start off just by refreshing our memory about what is voltage. So remember that a potential difference is what causes the force on the electrons in our electric circuit and what causes them to move. And we call that the electromotive force. So we used an analogy about pipes, pumping water around the pipes. So an analogy for voltage is the difference in pressure. So if we have a high voltage, you could think of that as like a high pressure difference in our pipes. So what would you guys think if you look at this picture of a waterfall, remembering our analogy we used last time about um, the height difference when looking at gravitational potential and the difference in voltage or the difference in electric potential when considering potential difference or voltage in a circuit. So if we have a quite high waterfall, we could say that there's a large height difference there, so there's a large difference in potential between the top and the bottom of that waterfall. So if we were to consider this waterfall as an electric circuit or as a part of our electric circuit, we would say that there is a large potential difference between the top and bottom of that waterfall. So there would be a large voltage between or across that point in our circuit. The next thing we talked about was amps, so electric current. So remember that electric current is the number of electrons that are moving around our circuit. It's the rate of flow of electrons, and we measure it in the coulombs of charge that are flowing past a point in our circuit each second. So we've got voltage, which is measuring how many joules each coulomb of electrons has, and we've got amps, which are measuring how much or how many coulombs of charge are flowing through our circuit. We're going to look at how we can combine those two to work out the rate of energy usage or the power in our electric circuit. So obviously we can only measure current or amps when our circuit is closed. So if we are looking at working on a problem and looking at how much power is being used or how much power is being generated in an electric circuit, we have to first check that our circuit is indeed closed. If it's not, then we won't have any current flowing, which means we won't have any energy transfer or we won't have any power being used in that circuit. The analogy for current or the analogy for amps that we used was if you've got a pipe, it's the actual amount of water that's flowing through the pipe. So if we changed from a small diameter pipe to a large diameter pipe, we would therefore allow more water to flow through it, which would increase the current, which would increase the amps if we consider it as an electric circuit. So how would we describe this river, thinking about, like we just talked about the waterfall analogy where we had a large difference in height from the top to the bottom of the waterfall? We said it had a large voltage. There's not really much drop along the length of this river that we can see in the photo, is there? So we would consider that there's quite a low voltage or quite a low potential difference between the sort of start and finish of the river that we can see here. But it does seem to be quite a large body of water that's flowing through there. So we would think that there's quite a lot of water that is flowing through this river. So we could say that this river has a low voltage, but has a large current flowing through it. But what about this waterfall? So this is the same waterfall in Yosemite National Park. It's pictured in two different seasons, one in summer and one in winter. Um, how would you describe the difference in the voltage and the amps, if this was an electric circuit, between those two pictures? So because it's the same waterfall, it must have the same height difference in both pictures. Therefore, the voltage is the same in both pictures. But we can see that on the picture on the left, there's quite a lot more water flowing over the waterfall than there is in the picture on the right. So we would say in terms of electricity, there's a lot more current flowing on the left-hand picture than there is in the right-hand picture. And if you were to think to yourself, well, which waterfall do you think then would be generating more power? If you were to connect a turbine at the bottom of that waterfall, which one would create more power? And clearly it would be the one on the left, because even though they have the same voltage or the same potential difference, the one on the left has much more volume of water flowing over it. It has a much greater current, so therefore it would produce a lot more power. So we use the unit of watts to measure power, to measure electric power, or any power, in fact, is measured in watts. It's the rate at which energy is being used or transferred or generated. So if we're thinking about a rate at which energy is being used, how could we turn that into a formula? So if we consider power, we know that energy is work that's done on something or done by something. So if we've got some amount of work or energy that is being transferred in some amount of time, to work out the amount of power, we just divide the work done divided by the time it took to do that work. So power equals work over time is the general formula for any situation where you're looking at power. So considering just an electric circuit, though, and looking at electrical power, if power equals work over time, so we remember from last lesson, we had that voltage equals the work done divided by the total amount of charge. So rearranging V equals W on Q, we can say that W equals V times Q, so work equals voltage times charge. So we can put that into the top of our fraction. So we have power equals voltage times charge divided by time. But we also know that current equals the amount of charge flowing past a point in a particular amount of time. So I equals Q on T was the formula we looked at last time. So substituting that into our formula for power, so if we have I equals Q on T, well, if we have P equals V times Q on T, that must just be P equals V times I. So electrical power equals voltage times current is our formula that we need to remember and that we're going to be using to calculate electrical power. You might be asked questions where it's like how much energy was used in this or to power this ceiling fan, how many joules of energy were used to power this air conditioner or something like that. So to work out the actual amount of energy or the work done, we can just multiply our power by time. So power equals work divided by time. Therefore, work obviously equals power multiplied by time. So the amount of work done is voltage times current and then multiplied by the time. So the amount of electrical energy used equals the voltage multiplied by the current multiplied by the time that was used for. Let's consider what is a watt. So if we're considering watts of electrical power in an electric circuit, a watt is, the formula for power, we've got power equals voltage times current. We know that the voltage is how many joules of energy each coulomb of electrons has, so volts equals joules per coulomb. We know that current equals how many coulombs are passing a point each second, so therefore I equals C coulombs per second. Putting those units into our power formula, power equals V times I, so we have joules per coulomb multiplied by coulombs per second. The per coulombs multiplied by coulombs, we end up with coulombs over coulombs, which cancels to 1. So we just are left with power equals joules per second. And that is the SI units for watts. So 1 watt of power equals 1 joule of energy transferred or generated or used per second. So 1 watt equals 1 joule per second. How would we describe this waterfall in terms of volts, amps, and power? it's quite a high waterfall, so you'd say there's quite a lot of voltage, there's a lot of potential difference between the top and bottom of that waterfall. It's quite a large waterfall, so there's a lot of water flow going over it, so we would say it has quite a high current. Therefore, the amount of power that this waterfall could generate would be quite high as well, because we have a large current multiplied by a large voltage. We would therefore end up with a large amount of power. So just a summary, we've got power equals work over time, where electrical power equals voltage times current, and the electrical energy used, or the work done, is the electrical power times time, or voltage times current times time. Please make sure that, as always, we use our SI units. If you get a question that says, someone runs an air conditioner for 7 hours on a particular day, you need to convert that units of time into seconds to work out how much energy was being used. So always making sure that our units are converted back into SI units. It's quite common to use prefixes for power. If you're considering like the power that's used in your phone or your AirPods or something, you'd be talking in terms of milliwatts of power, because there wouldn't be very much current flowing through those devices. If we look at like air conditioners, things like that, they commonly use kilowatts of power or thousands of watts of power. And then if we start looking at power stations and how much power is being generated in a power station, they would be generating megawatts or millions of watts, or even gigawatts, which is billions of watts, 10 to the power of 9 watts. So the worked examples from the text, page 222, an electric heater has power of 2 kilowatts. So it's rated, the electrical heater is rated at 2 kilowatts. That means it draws 2,000 watts of power. So that's the first one, 2 kilowatts. Kilo is the prefix for 1,000, so it's 2,000 watts. And how much energy would the heater use if you ran it for 10 minutes? Power equals work on time. So as we said before, work equals power multiplied by time. You have 2,000 watts. And again, as I said, make sure you convert your units of time into seconds. Otherwise, you're going to have a bad time. So we have 10 minutes times 60 seconds, or 600 seconds. We would have 1.2 million joules, or we'd probably write that as 1.2 megajoules, or 1.2 times 10 to the power of 6 joules of energy used by that heater. Next example, 7.4b. Determine how much current is flowing into a toaster that has a rating of 1200 watts and is connected to a 240 volt power supply. So this one, we're just rearranging our power formula. If our toaster is going to draw 1200 watts of power, it's using a 240 volt power supply. That means it's going to be drawing 5 amps of current out of your home circuit. And lastly, example C, 7.4c, how many joules of electrical energy are transferred per second by a 6 volt 0.5 amp lamp? So for this one, energy transferred per second, it's actually asking for power. So I don't really, his answer, he's just given how many joules are transferred, which, I mean, I guess technically that's okay, but if you ask for how many joules are transferred per second, it's asking for power. So you can see it's kind of erroneous to multiply by 1 second at the end there, because we have 6 volts times 0.5 amps would give us 3 watts of power. And if we have 3 watts of power over a 1 second period, then that's obviously going to be 3 joules of electrical energy. So this, the example 7.4b, that's kind of an interesting one. I don't know if many people have know that in America they don't really use electric kettles to make coffee or to make tea or anything like that. They use ones that are, you might have seen in movies or on TV, that they use ones that they put on their stove, or they heat their water in the microwave, or use those drip filter coffee machines. So the reason for that is in America their home electricity supply is only 110 volts. So if we were to think about it in terms of the rate of power that we're using, let's say for the sake of argument that it's a 1200 watt kettle, and we wanted to boil some water in that kettle in America versus in Australia. So your home circuits are limited to how much current that they can put out. So if you wanted to boil water in America and using a 110 volt power supply, to get the same amount of energy transferred, the work done on the water, is going to take twice as long, or just over twice as long as it does if we're in Australia using a 240 volt power supply. So that's kind of a bit of trivia as to why most Americans don't use electrical kettles to heat their water. So there's some links there if you're interested in looking at generating electricity and how power is generated to power our cities, and also an example looking at mechanical power. So we've just been looking at electrical power, but often electrical power is converted into mechanical power using motors. So that's something that we'll look at a bit later on. So, can you guys describe the meaning of the power formulas? The formula and data book only include power equals work divided by time and power equals voltage times current. So if you are asked to work out how much energy is used in a particular amount of time, or the work, you're asked to calculate the work, then you just need to remember that work equals power times time, where power is VI. So we could have work equals voltage times amps times current. So you can now go and spend some time doing Check Your Learning 7.4. As you have all this week, you've got work assigned on Education Perfect and CK12. We're now finished Chapter 7, so you can go and have a look at the Chapter 7 review questions. And next time we're going to get into Chapter 8. Thank you very much.